Hello everyone, my name is Esmaeil Mirvakili, a second-year PhD student at UCSC. My project is managing the Bufferbloat in storage systems. In computational storage system, we designed a storage server with different multiple layers with queuing, so we can make the storage system more scalable. Front end is usually responsible for higher abstraction for storage, like objects. And the backend is basically wrapping the storage device and responsible for uh, lower level of operation like block operations. In computational storage systems, scheduling is really important. Usually we have different user with different quality of service requirements, and we want to meet all of those requirements. The scheduling is usually happening in the front end because we don't want the scheduling system be engaged in storage device details or lower level details. And also we want to do the scheduling at the user request levels. So it's happening in the front end. And sometimes it's not really possible to do it in the back end. But there's the issue here. Basically, the front end submit the request as a batch to the backend, so it can be processed as a batch and increase the performance and all of the non-functional requirements. But the problem is that if these batch are really small, so we won't be able to utilize the storage device at the maximum capacity. But there is another problem if the batch are very, very big. In the picture, you can see a few requests in the front end and back end. The red one are the requests with very high priority, the yellow are medium priority, and the blue ones are the low priority. When a front end submit a batch, every request that come to front end should wait until this batch is done. So basically, when a higher priority requests come to front end, should wait until these low priority requests are done, which can violate the quality of service. And if this batch size is very big, this problem can be really affect the quality of service and the overall performance of the scheduling. So the question is that which batch size is proper for the storage systems. What we did is that to look at this problem at a different angle. We discovered that the Bufferbloat problem in the storage in the network system is really similar to our problem. Basically, when there is a buffer or a queue and the upstream just submit too many requests and too many data to this buffer, we will have some spikes in latency because the request will have to wait in these buffers and will usually take a bit time, which we call it queue delays. This is really common in networks, and it is solved in networks, which is really interesting to us because if you look at this our problem as a Bufferbloat, so there is a lot of solution to that right now. And the solution is about to limiting these incoming data from the upper stream and limiting the amount of that data. So our goal of project is that to design an admission controlling backend to control the batch sizes, basically create a back pressure mechanism in the backend. By doing this, we are trying to minimizing the queuing delay in backend, but we really need the acceptable throughput. We definitely don't want to compromise the throughput at all, but we might be able to sacrifice a little bit of throughput to achieve the schedulability for a storage system. By minimizing the queuing delay, we are going to have as many as possible requests at the front end for scheduling. So the problem with the high priority requests can be solved by this. The other goal is that we need to adapt this batch size based on the workload and the underlying device. Different workload and the different devices can have different impacts on the scheduling system. So we want to consider that that the batch size should be suitable for different workload and different devices. At the end, we want to implement a scheduling algorithm in the front end that uses the backpressure in the backend. The well-known solution to Bufferbloats in network is CoDel algorithm or control delay algorithm. Copel is a scheduling algorithm. It was proposed to solve the Bufferbloat in network. You can see the general form of the algorithm. This algorithm have two important parameters: interval and the target delay. Basically, this algorithm keep track of the queuing delay in the interval, and at the end of every interval, it just compare the minimum queue delay with target delay. If it is more than target delay, so it's considered as a violation, and it's going to decrease the batch size or limit the incoming rate. Otherwise, it's going to increase the batch size, assuming that it has the capacity to increase the rate. So we wanted to implement the CoDel for the storage system. So we went for the Ceph. Ceph as a distributed storage system has the same problem. At the storage servers, there are OSD that operates at the object level. They store the object requests from the users. And the BlueStore as a backend operate at the block level for the storage device. And the Ceph, as I mentioned, has the same problem, and which is the OSD submitting too many jobs to BlueStore. Basically, it's shovel every request that it receives to the BlueStore. As we can say, the BlueStore has a unlimited buffer. So we want to implement the CoDel for the Ceph. For designing our own version of CoDel, we needed to experiment multiple times on BlueStore. To simplify things, we implemented a simulation for BlueStore. For that, we simply ran the workload of 4 kilobyte writes, which is an important and well-known use case for BlueStore on the SSD devices. And we measured the latency of different components inside the BlueStore. And then by having these measurements, we create an overall latency model for BlueStore, how different requests and different writes works on the BlueStore and how much time they will take. So we created simulation based on this model, and we try to experiment the CoDel on this simulation. And at the end, we come up with this algorithm that I don't really want to get to details how we get here, but for violations, basically, we calculate the error between minimum queue delay and the target delay and update the batch size according to that error. And for increasing the batch size, we simply increment the batch sizes by considering the limit and upper bound to the batch size. Here's the result of simulation, some of the results. On the left side, you can see the baseline, the regular BlueStore simulation without CoDel. And this basically this chart is showing the queuing delay inside the BlueStore, how much time every request spent in queue waiting for processing. And on the right, you can see the same simulation, but this time with the CoDel algorithm in place. The CoDel parameter was 500 microsecond for target delay and also 1 millisecond for intervals. The result was that there was a 6% drop in throughput and more than 25% drop in queuing delay. This really easily show that how CoDel works here. Basically, it decreased the queuing delay, but it introduced an overhead and introduced the drop in throughput. But 6% can be acceptable by achieving 20% drop in queuing delay and make this, for example, schedulable. We might be able to accept this drop in throughput. For showing that how these parameters affect the result, I have another result for this time for target delay of 300 microseconds instead of 500 microseconds. The drop in throughput was increased, but we achieved even more drop in queuing delay, which was really interesting. And here's another result with different interval. Basically, interval shows that basically if you choose a very, very big interval, we won't be able to identify the violation like here, that I choose an interval of 1.5 milliseconds. And as you can see, the drop in queuing delay was not really continuous. And some part, the violation was not detected correctly. So all we have to do is finding the true parameters and correct parameters for CoDel for different situations for the storage system. So we have acceptable throughput loss, but a good amount of decrease in queuing delay, so we can make the scheduling work. After that, we implemented this version of CoDel on the BlueStore, and we ran the same experiments on them. Here's are the results. These are the early results. We are still experimenting with the BlueStore with CoDel. The same as before, the left side is the baseline, the regular BlueStore, and the right side is the BlueStore with CoDel. With these settings, target delay of 1 millisecond and interval of 1 millisecond as well, we had 13% drop in throughput and 20% drop in queuing delay. It was a little different from simulation that we expected, but as I mentioned before, the simulation was the simplified version of BlueStore. So we expected a little differences. Now we are working on the BlueStore implementation to find tweak the CoDel a little better and change the settings. Here's a different result for this time 800 microsecond, that we had even more, twice as more drop in throughput. And the ongoing and future works are here. As I mentioned before, we are experimenting with CoDel in BlueStore to understand the behavior of CoDel and find a better version of that. Also, we are studying how these parameters, the target delay and the interval, how they are sensitive to workload and different devices. And we want to see if a specific configuration for CoDel works with different workload and devices or not. And also, we really want to consider alternative algorithm and design for CoDel that is out there. There's a different solution for Bufferbloat. We want to go over those solutions as well. And also, we want to see if we can adapt these CoDel parameters to dynamic workloads. If we need different configuration for CoDel for different workloads. So we want to see if it's possible to adapt these parameters automatically by the dynamic workloads. And the very interesting things is that basically the CoDel or the backpressure mechanism in the backend system that can provide us with very valuable information about workload, different requests, and the different latency inside the backend. So we can use those information in front end to schedule the request more intelligently. And we are really looking forward to that. And thank you, everyone. If you have any questions, feel free to ask.